Hello all. Welcome to this interesting video session on conservation of angular momentum. So this concept is very important as far as any revolving bodies are concerned, especially in space dynamics. So this concept is also very important, especially when we try to understand Kepler's second law of motions, okay, regarding to planetary motion. So the Keplerian laws are very important. We have seen the first and third. So before going to the second law, it's important to know what is conservation of angular momentum and how it plays an important role. Okay. Now, as we have seen in our previous lectures, we have a small mass, or let's say it's a bigger mass. Okay, slightly bigger mass this time. So slightly bigger mass of m, and here it is a small m again. Okay. Now let's say this is not that much big, but still we consider some point masses, okay? So these two are some point masses with respect to each other, okay? You can take either this as big or this as small, so it's up to you in this context, okay? Now let us understand we have a uniform path where it is been separated, so it exhibits a uniform motion. So the first assumption is we go with a uniform motion, okay? We go with a uniform motion. And now let's say this is traveling maybe to the next position. Let's say this is our next position, and now you draw a line like this. And as usual, we draw a straight line to make this curve a bit easy to solve, okay, to reduce the complexity. So now we have a right angle, and now we have a small angle called the d theta. Okay, so this similar diagram we have already seen in our previous lecture video. So those of you not watched the video, please try to watch it and gain some insights also. Fine. So for any revolving body, we know that your centripetal force, okay, this time we'll try to make it very simpler, okay. Your centripetal force is equal to the mass times acceleration, is called the centripetal acceleration, because this is basically the Newton's first law. Force is equal to mass times acceleration, and here this is centripetal acceleration, so we go with the centripetal, has this is centripetal force, so we go with the centripetal acceleration. So sorry, my mistake. So when I try to explain certain steps, I go by some mistakes, so make sure that you follow my writing accordingly, okay. So if at all any confusion, probably you can refer my writing, so that won't make some confusion, okay. So once again, as per Newton's law, F is equal to ma, and centripetal force is associated with centripetal acceleration. Well, that is fine. So now we have the centripetal acceleration is given by. Now let's say we are more interested in the revolving mass, okay, as already we have taken. So that is the basics. Always you consider the revolving mass, and this is called the fixed mass, which is taken as a frame of reference, okay. Now AC is equal to, okay, V, okay, V square divided by R. So here it is the revolving orbital speed and divided by the distance. Maybe it's called the R. So we go with V square by R. Okay. Now we substitute Fc is equal to mv square by R. Okay. Now in your elementary classes you have learned what is an angular momentum. So angular momentum is basically when you try to do angular momentum. Okay, this is basically in space mechanics. We normally denote angular momentum as h. Okay, now we denote this as h. So h is given as your rotational analog of the linear momentum. Now let's say if this is a linear momentum which is rotating at some radius of something of r, let's say, so into r. Okay, now we'll take only the magnitude. We won't go with any vector rotations. So r can be a perpendicular distance, okay, whatever may be. So now your h is equal to mv, which is the basic formula for momentum, okay, p is the momentum, so into r. So basically r is actually a direction which is perpendicular to the momentum, okay, mass into velocity. Okay, so h is equal to mv here. So this is called the magnitude wise, this is called the angular momentum expression. Okay, now let's say we have mv square by r here. So I write fc is again equal to, okay, now fc I have very much important term here. So fc is equal to m into, we have m into v, okay, mv divided by r, Okay, now I take the V separately. Okay, I need to do some small adjustment over here. Now I multiply both R and divide this by R. Okay, now I can group the term. FC is equal to MV into, I'll take 1R here. Okay, I'll take 1R here. So divided by R square, okay, into V. Okay, I think this is pretty much clear for you. Okay, you have MV here, you have R here, so I have written MV here. We have V here, so I written V here. So this is R by R because we multiply and divide by R. Okay, so that gives me MV square by R. So FC is actually is equal to H into V divided by R square. I think this is clear. HV divided by R square. Okay, now we know that for any rotating mass, okay, so for any rotating mass which experiences a centripetal force towards in this direction, towards the center, normally the weight is going to pull. Okay, so your weight is actually mg, so this smaller mass is having m, and the acceleration due to gravity is actually pulling this object towards the center, so that is called the weight. So against the weight is trying to rotate it. Okay, so your weight is actually balanced by the centripetal force. Okay, now again, a g value depends upon what planet or what mass that you are going to take. So we have, in fact, what type of planet you are going to take, if it is a Jupiter or if it is a Earth, okay, if it is a Sun, so it depends. Now in this context, we'll try to take this as an Earth and this as a satellite or something. So probably I go with g value as per Newton's law of gravitation, your g, acceleration due to gravity field, which is given by gm by r square. So it is nothing but the gravitational force. Again, if you rewrite and observe closely, this is nothing but your gravitational force, where the two masses has been separated by a small distance r. Okay, so your force of gravitation is the proportionate to the product of mass and inversely proportional to the square of the distance between them. So that is called the Newton's law of gravitation, which is called gmm by r square. Now I equate. Okay, this time we'll take only the magnitude wise. If you apply the magnitude wise, everything is going to be positive. We are not worried about any direction or something, because ultimately we want to equate the two terms. Okay, so gm by r square. So if it is again negative, also negative, so it get cancelled. So anyway, we're going to take the magnitude term. So gmm by r square, that should give me something called h into v by r square. Okay, h into v by r square. I hope this is clear for you. So if you want to analyze once again, you can go here and you can cross check whether we have made any mistake. So we have mv into v into r by r, so mvr. Okay, so mvr into v divided by r square. I just want to make sure that we are not committing any sort of mistakes. Okay, and now let's say you have gm. What is gm? It is, you know, gm is actually called the gravitational parameter. Okay, gravitational parameter denoted by the symbol mu. Okay, so which is again a constant which you can refer the data book prescribed by your textbooks, university textbooks, in fact, or any data book related to space mechanics. So now you have mu here, and now you can write mu into a finite mass m. So that should give me h into v. Okay, because your r square is getting cancelled off, so you don't have to consider any sort of r square. So I think this is much more important, because your r is not longer exist here. But when we have the velocity, okay, when we try to do the velocity over here, okay, now let's say we have some velocity which is being exhibited. Okay, now the velocity is again given by the expression v is equal to root of gm by, okay, now here is a distance of separation is r actually. Okay, so here point mass we have taken, so we are not worried about the smaller radius. And also, as a simplicity, we always assume your r is greater than the radius of the bigger planet and the radius of the smaller planet. Okay, just for simplicity. Now gm by r we'll just take here. Okay, that is the distance, because whenever we consider with the rotational body, we always take the distance between the two planets, that is r. So you get v is equal to gm by r. Okay, I can again write this expression, v is equal to root of mu divided by again r. Okay, now I can write your, now if I substitute in this direction, in this let's say in this equation, okay, so we have mu of m, which is equal to, we have h, which is angular momentum, and what is v here? We have root of, so here I am making again, gm is actually your mu term, so root of mu divided by r again. Okay, root of mu divided by r, and now again your if I cross multiply or do the simplification, you get something like mu m, okay, into root of r divided by again root. It's just a simple math we have done here, nothing else. We have not gone for any complicated stuff. Okay, so I think this is clear. You have taken root r this side, you get um into root r, so root mu of mu comes in the downside, so it comes to here. So now you have what is mu actually. So mu can be written as, in fact, it is the root of mu times into root of mu into m into root of r divided by root of mu. So you get an opportunity to cancel one root of mu, so, and that should give me h. So root of mu, okay, into r, okay, and that times will give me some mass over here, so that should give me h. Now if you are exhibiting a constant speed, okay, now let's say we have a radius or something, okay, now this radius is having a value of r or something. Now what we do is, like, we differentiate. Okay, now we take something called dh. So dh, okay, dh if you take, so if you differentiate, we get m into root of mu. Okay, root of mu will get, so now into, so this is r to the power of half, you get half into, okay, half into root of mu. Okay, because it is basically, if you know that your elementary calculus, d by dx of any x power half is nothing but you take half here and you deduct 1 here from half, so x power half minus of 1, it's again minus 1 by 2, which gives me 1 by 2 into root of x. Those similar values I have written over here. Okay, it's a small calculus we have done here. So into dr we are going to get, okay, this is actually r, so you not get confused. So this is into dr will get, okay, now dh, which is equal to mu into root of mu into half into dr, okay, into 1 by root of r. So this is the expression that you are going to get. So now we divide this entire term with a small time interval dt. So this is happening at a very small time interval dt. Okay, so now let's say dh by dt. So I write dh by dt is equal to m into v root of mu into half into root of r. I just group the term root of r. Okay, so this is m root of mu into 1 by 2 into root of r into dr divided by dt. Now you have to be very careful here. Your dr by dt here, if you see, if any motion is a constant, moving with a constant velocity, then probably dr by dt is going to be 0, because for any constant uniform velocity, okay, now we have already assumed that your body is in a uniform motion. So in that condition, your dr by dt is actually 0, so it is going to be execute a uniform motion. So this turn is going to be 0, so ultimately you end up with, okay, ds by dt equal to 0. Okay, because ds by dt is equal to m into root of mu into 1 by 2 root of r into dr divided by dt. So dr by dt is 0 because we have a constant uniform motion which is coming into picture. So your velocity will be going to be 0 here. Okay, so 0 times this entire term is going to yield me 0 again. So that means your d of h is equal to 0 again. That implies when any quantity of your dx, when any quantity, let's say is going to be differential is going to be 0. Differential of any quantity is going to be 0. That means that quantity yields 0 because differential of any constant is actually 0. So that implies your h value is a constant for this planetary motion. Okay, that means it is moving at a constant acceleration, and it in turns gives me an important concept called the conservation of angular momentum. That means that for any path, let's say in a uniform motion, the angular momentum is constant. Okay, for any planet which is revolving around another planet with some frame of reference. So that is called the conservation of angular momentum applied to your planetary bodies. So here your dh is by dt is 0, so that means your h is going to be constant. Okay, now I'll take one more modification here. You know this h is actually m into v into r, which we already know. Okay, because your momentum is applied at a certain axial distance of r or something, a path. So that is actually going to be a constant. Okay, if mv into r is a constant, that implies, okay, you can write your v equal to r omega. If you substitute here, you are going to get m into r square into omega, which is again a constant. Okay, which is going to be again a constant. Again, your mass, we know the mass of the system. So if you take this into the denominator side, okay, this time, so again you are going to get again a constant term. So ultimately we end up with omega into r square is going to be a constant. Okay, omega into r square is going to be a constant. Okay, so that means your h by m is actually a constant. That means the specific angular momentum is going to be a constant. So this also yields me an important expression called omega r square is going to be constant for any location. Okay, for any location in a orbital, let's say orbital position, okay, of any planet which is been revolving. So in that condition, these two concepts apply very interestingly. Okay, so this is called the law of conservation of, and this is called the law of conservation of angular momentum. Okay, okay, so this is called the law of conservation of angular momentum, and we write mv is going to be a constant, and which also yields me omega into r square is again a constant. Okay, so hope you have enjoyed this video. So try to practice this, because we are not dealing with any sort of complexity here. We are trying to make things at most simpler so that you can understand, you can apply wherever you require. So I hope this is informative video for you, and we'll see you in the next video. Thank you so much.